Tonight, we're going to look at something most people have never thought to look at closely. A small moon, pale, smooth, orbiting Jupiter in silence. For centuries, Europa was just a point of light in the outer solar system. A cold, frozen object too far from the sun to take seriously. But here is what most people do not realize. Beneath Europa's cracked ice surface lies an ocean. A real liquid water ocean. One that may be twice the volume of every ocean on Earth combined. And it has been sitting down there in total darkness for hundreds of millions of years. By the end of tonight, you're going to understand what the James Webb Space Telescope detected when it pointed at Europa for the first time, what that detection says about the chemistry happening inside this moon, and why the answer it produced is not the simple, hopeful story that headlines described. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It is a simple action, but it helps this channel reach more curious minds like yours. Now, let us begin. There is a telescope currently parked 1.5 million kilometers from Earth, not orbiting above the atmosphere, not resting on a mountaintop. It is sitting at a gravitational balance point in deep space called the second Lagrange point, where the combined pull of the Earth and Sun holds it in a stable position without needing constant fuel. It is a quiet place to work, cold and still, far enough from Earth that our own planet's warmth does not interfere with the readings. The James Webb Space Telescope has been operating there since early 2022. Its primary mirror is 6.5 meters across, made from 18 hexagonal segments of a metal called beryllium, each one coated in a thin layer of gold. The gold is not decorative. Gold reflects infrared light with exceptional efficiency, and infrared is what Webb was designed to collect. Infrared light is invisible to the human eye. It sits just beyond the red end of the visible spectrum, in a range that carries heat signatures, molecular fingerprints, and the chemical imprints of substances that interact with light in ways our eyes were never built to see. Earth's atmosphere absorbs most of this infrared light before it reaches the ground, which is one of the reasons Webb had to leave Earth entirely to do its work. The telescope was built to look at the deep universe, to gather light from galaxies so far away that it left them before our solar system existed, to peer through vast clouds of dust surrounding newborn stars and photograph the planetary systems forming inside, to read the chemical composition of atmospheres on worlds orbiting distant suns. And then, in September 2022, something changed. The telescope was instructed to turn and point at Europa, not a distant galaxy, not a star nursery light years away, a moon, one of Jupiter's moons, roughly 628 million kilometers from Earth. A frozen world orbiting a gas giant we've been watching with our naked eyes since ancient times. To a telescope capable of photographing the first light of the universe, pointing at a moon in our own solar system might seem like using a powerful microscope to read a newspaper. But that is exactly the wrong way to think about it. Webb was pointed at Europa for a reason, a specific, deliberate reason. Scientists wanted to know whether the surface of Europa carried any chemical signature from the ocean they believed was sitting underneath it, whether the ice had been stained in some way by chemistry rising from below. The observation window was 53 minutes. In that time, Webb's spectrograph collected infrared light bouncing off Europa's surface and split it into its component wavelengths. The result was a spectrum, a chemical fingerprint, a record of which molecules were present based on the specific patterns of light they had absorbed. This is what spectrometry does. Every molecule absorbs light in its own characteristic way, at its own specific wavelengths, like a voice recognizable not by sight but by the exact frequencies it produces. A spectrograph does not need to touch a substance to identify it. It reads the light the substance leaves behind. Previous telescopes had attempted this at Europa, but their resolution was limited. They could gather the average signature of the whole surface, everything blended together. What Webb could do was different. Its combination of mirror size, detector sensitivity and precision allowed it to map chemistry to specific regions of the surface, to hear not just the overall voice of the Moon, but distinct voices coming from distinct places. And in September 2023, when the results were published in the journal Science by a team led by Geronimo Villanueva at NASA's Goddard Space Flight Center, what Webb had detected over one specific region of Europa's surface was carbon dioxide. Carbon, on Europa, directly observed, precisely located. That sentence needs a moment. Carbon is the atom around which all organic chemistry is built. Every living thing on Earth, every protein, every DNA strand, every cell membrane is built on a carbon backbone. Finding carbon on a moon that already had strong evidence for a liquid water ocean beneath its ice is not a routine detection. It is the addition of one more ingredient to a list that was already causing serious scientific attention. But the carbon itself was not the finding that mattered most. What mattered was where it was concentrated. Europa's surface is not chemically uniform. When Webb mapped the carbon signal across the Moon's surface, the reading was not evenly spread. It was not scattered randomly. It was not clustered near the poles or near old craters where space rocks might have delivered it from outside. It was sitting directly over one specific region, and that region had a name. Europa's surface, seen at high resolution, is not the smooth white ball most people imagine. It is fractured, complex, crossed by long, dark streaks that run for thousands of kilometers, interrupted by zones where the ice has broken apart and refrozen in chaos, stained in browns and oranges and pale yellows from minerals carried up from below and then chemically altered by radiation from above. The long dark streaks are called lineae. They form when tidal stresses crack the ice shell, and material from inside the Moon wells up into the gap before refreezing. They record thousands of years of geological activity written in ice. The disrupted zones are called chaos terrain. These are regions where the disruption was not just a crack but a collapse, where large sections of the ice appear to have broken apart, shifted sideways, and been surrounded by refrozen slush before the cold locked everything into place. They look like photographs of a frozen sea mid-storm, stopped suddenly and preserved. One of the most prominent of these chaos regions is called Terra Regio. It sits in Europa's leading hemisphere, the side that faces forward as the Moon orbits Jupiter. It is roughly 1,800 kilometers across. To put that in perspective, that is wider than the distance from New York to Denver. It is enormous, and it is geologically young. The surface of Terra Regio shows fewer signs of secondary processing than older regions around it, which means whatever disrupted it happened more recently in geological terms. Webb's spectrograph found its highest concentration of carbon dioxide sitting directly over Terra Regio, not near it, not adjacent to it, directly over the youngest, most recently disrupted, most geologically active major feature on the surface. Now consider what that means. If the carbon had arrived from space, delivered by comets or asteroids striking the surface over billions of years, you would expect it to be spread more randomly. Impacts do not politely concentrate their deliveries over specific young geological features. You would also expect older surfaces to have accumulated more material than younger ones. The opposite is true here. The younger surface has the most carbon. If the carbon was manufactured by radiation acting on the surface ice, you would expect it to correlate with the radiation environment, which varies with latitude and orientation, not with specific geological features at specific locations. The pattern that JWST measured points at one explanation more than any other. The carbon came from below, It was carried upward through the ice shell by the same geological process that disrupted Terra Regio. The chaos terrain is not just a surface feature. It is a scar left behind when material from the ocean beneath pushed upward strongly enough to crack and displace the ice above it. And that material carried chemistry with it, including carbon. Geronimo Villanueva and his colleagues at Goddard were precise in their published language. They wrote that the distribution of CO2 was consistent with an origin in Europa's carbon-containing subsurface ocean, delivered to the surface through geological activity in the ice shell. They were careful to note that abiotic chemistry with no biological involvement whatsoever, could fully account for the carbon dioxide. They were not claiming life. They were claiming something more specific and more foundational. The ocean beneath Europa's ice is in chemical communication with the surface above it. Material flows between them. The interior is active enough to push its chemistry upward through kilometers of ice and leave it on the surface where a telescope 628 million kilometers away can detect it and map it. That is the observation. The ocean is not sealed. It is not isolated. It is talking, and the first word it sent was carbon. Before we can understand what that carbon means, we need to know what we're dealing with beneath the ice. Because the ocean of Europa is not a hypothesis that scientists are still debating. It is confirmed. The confirmation came not from drilling through the ice or sending a probe into the water. It came from a spacecraft that never touched the ocean at all. In the mid-1990s, NASA's Galileo mission arrived at Jupiter after 6 years of travel from Earth. Galileo spent years in orbit around Jupiter, conducting repeated close flybys of the 4 large Galilean moons. During its Europa passes, one instrument in particular returned data that stopped the planetary science community in its tracks, the magnetometer. Jupiter has one of the most powerful magnetic fields in the solar system. Generated deep inside the planet by convection in metallic hydrogen, it extends millions of kilometers in every direction, filling the space around Jupiter with a vast magnetic environment. When this rotating magnetic field sweeps past a nearby moon, it does something predictable. It induces a secondary magnetic field inside any conductive material it encounters. Think of a metal detector. You pass it over the ground and it sends a magnetic signal downward. If there is metal buried below, the signal induces electrical currents in the metal, and those currents produce their own detectable response. The detector never touches the metal, but the response reveals it. Galileo's magnetometer was doing something similar at Europa. When the spacecraft made its close passes, the magnetometer detected a secondary magnetic field being induced inside the moon. The strength and character of that induced field was carefully analysed by Margaret Kyvelson at UCLA and her colleagues, and the result was clear. Rock alone, the silicate minerals making up Europa's interior, was not conductive enough to produce what they were measuring. The signal required a layer of something far more conductive, something sitting close to the surface, something global in extent. Salt water conducts electricity. A worldwide ocean of liquid salt water, sitting beneath a relatively thin shell of insulating ice, would produce precisely the induced magnetic field that Galileo's magnetometer recorded. That was the confirmation. Not a physical sample, an electromagnetic reading, but one that was consistent, repeatable across multiple flybys, and not explainable by any other reasonable combination of materials and structures. The surface geology supported it. Europa has almost no craters. The solar system has been raining impactors on planetary surfaces for 4.5 billion years. The Moon, which has no active geology, is covered in craters recording billions of years of bombardment. Europa should have collected a similar number of impacts over the same time span. Instead, Europa's surface looks almost new. its average surface age is estimated at somewhere between 40 and 90 million years. In a solar system 4.5 billion years old, that is geologically recent. Something has been continuously erasing the old surface and replacing it with new ice. That something is the ocean below, driving geological activity in the ice shell above it, renewing the surface from underneath. Now consider the scale of what that ocean contains. The ice shell above it is estimated at between 15 and 25 kilometers thick. Below it, the ocean begins and extends downward for an estimated 100 to 170 kilometers. Earth's ocean has an average depth of about 3.7 kilometers. The Mariana Trench, the deepest point on Earth, reaches not quite 11 kilometers. Europa's ocean is more than 10 times deeper, and it covers the entire Moon. The total volume implied by those dimensions is roughly twice the combined volume of all Earth's oceans. The Pacific, the Atlantic, the Indian, the Arctic, the Southern Ocean, every drop of seawater on the surface of our planet, doubled, and sitting in total darkness beneath 20 kilometers of ice on a frozen moon orbiting Jupiter. This is not a small body of water. This is the largest known reservoir of liquid water in the solar system, and JWST has now confirmed that it is chemically connected to the surface above it. Knowing that the ocean exists and that it is communicating with the surface raises an immediate question. What keeps it liquid? Europa is 628 million kilometers from the Sun. At that distance, sunlight arrives at less than 4% of the intensity that reaches Earth. That is not nearly enough heat to keep a global ocean liquid inside a moon in the outer solar system. If solar warmth were the only heat source, Europa would be frozen solid from surface to center. The heat comes from somewhere else, from Jupiter, not from Jupiter's light, from Jupiter's gravity. Europa's orbit around Jupiter is not a perfect circle, it is slightly elliptical. That ellipse is not a coincidence or a temporary state that will gradually smooth out. It is maintained by a gravitational relationship that links Europa to two other Jovian moons, in a pattern called the Laplace resonance. The Laplace resonance is a precise orbital synchronization. For every single orbit that Ganymede, the outermost of the three, completes around Jupiter, Europa completes exactly 2. For every orbit Europa completes, Io, the innermost, completes exactly 4. A 1 to 2 to 4 rhythm, locked in place by the moon's mutual gravitational interactions, self-sustaining, stable over geological time. This resonance prevents Europa's orbit from settling into a perfect circle. And because the orbit is elliptical, Europa's distance from Jupiter changes slightly over each 3.55-day orbital period. When Europa is closer to Jupiter, the gravitational pull on it is stronger. When it is farther, the pull is weaker. Gravity does not pull equally on all parts of an extended object. The side of Europa facing Jupiter at any given moment feels a slightly stronger pull than the center, and the center feels a slightly stronger pull than the far side. This differential, called a tidal force, physically stretches the moon in the direction toward and away from Jupiter. As Europa travels along its elliptical path, this stretch changes in magnitude and direction on every orbit. The moon is repeatedly deformed, squeezed and released, its interior rock and water flexed in a rhythm that has been running for hundreds of millions of years. Repeated deformation of any material generates heat. This is a simple physical fact. When you bend a piece of metal back and forth quickly, it warms at the point of flexing. When you squeeze and release a rubber ball rapidly, the rubber heats up. The mechanical energy of deformation is converted into thermal energy, applied to a moon-sized body over hundreds of millions of orbital cycles. This conversion generates an enormous amount of heat. Current estimates put Europa's tidal heating output at somewhere around 100 billion watts, continuously. To understand that number, consider that the total electrical generating capacity of the United States, from every power plant and solar panel and wind turbine and hydroelectric dam combined, is roughly 1,100 gigawatts. 100 billion watts is 100 gigawatts. Europa's tidal engine is producing heat equivalent to nearly a tenth of the entire US electrical grid, from inside a frozen moon, not from any fuel but from the simple, rhythmic squeeze of gravity. And it has been doing this for a very long time. The Laplace resonance that maintains Europa's elliptical orbit is self-sustaining. The Moon's gravitational interactions reinforce the orbital configuration every time any of them tends to drift. There is no sign it will end on any timescale relevant to biology. The ocean on Europa has almost certainly been liquid for hundreds of millions of years, perhaps for billions. That has consequences. If life needs time to get started, Europa has had that time. More time, in fact, than complex animals have existed on Earth. The ocean did not form recently. It was not a temporary accident. It is a structural feature of this moon's existence, written into the orbital mechanics of the Jovian system, guaranteed to persist as long as Jupiter's gravity operates and as long as the resonance holds. Which raises the next question. If gravity keeps the ocean alive from below, what is happening to Europa from above? Europa does not orbit in a quiet, protected region of space. It orbits inside Jupiter's magnetosphere. Jupiter's magnetic field is one of the most powerful structures in the entire solar system. Generated by convective flows of metallic hydrogen deep inside the planet, it extends tens of millions of kilometers in every direction. If you could see it from Earth with some instruments sensitive to magnetic fields, it would appear roughly 5 times larger than the full moon in the sky, despite Jupiter being hundreds of millions of kilometers away. Inside this magnetosphere, charged particles are continuously accelerated to high energies. Electrons and ions, many of them originating from sulfur and sulfur dioxide, ejected by Io's volcanoes and then ionized by Jupiter's radiation, spiral along the magnetic field lines at tremendous velocities. They form radiation belts around Jupiter, similar in principle to Earth's Van Allen belts, but vastly more intense. Europa orbits within these radiation belts. The numbers are not gentle. The surface radiation dose on Europa is estimated at roughly 540 rem per day. A single acute dose of 400 to 500 rem is enough to be lethal to a human being without immediate and intensive medical treatment. Europa receives more than that every day. An unprotected astronaut standing on Europa's surface would accumulate a fatal radiation dose within a matter of hours. Any spacecraft visiting Europa requires careful radiation hardening of its electronics simply to survive. The ice shell provides significant protection to the ocean below. Radiation penetrates the surface ice to a depth of perhaps a meter or two before being largely absorbed. The ocean, tens of kilometers beneath the surface, is shielded, but what the radiation does to the ice it passes through is not passive. When high-energy particles strike water ice molecules, they carry enough energy to break the chemical bonds holding those molecules together. Water, H2O, is split apart. The fragments recombine in new configurations that were not present in the original ice. Over geological time, this process, called radiolysis, builds up a significant inventory of new chemical compounds on Europa's surface. Hydrogen peroxide is one of them, molecular oxygen is another. Sulfur compounds, sourced partly from Io's volcanic emissions drifting across the Jovian system and falling onto Europa, are chemically modified and incorporated. These compounds are oxidants, molecules carrying chemical energy in the form of a readiness to react, to transfer electrons to or from other substances. On Earth, the deep ocean receives oxidants from above in the form of photosynthetically produced oxygen. Sunlit organisms at the ocean surface split water molecules, releasing oxygen that dissolves and drifts downward, providing chemical energy to organisms living in depths where light never reaches. The energy chain starts with sunlight at the top and flows down. Europa has no sunlit surface layer. No photosynthesis is possible anywhere on or near it. But radiation is doing something at Europa's surface that may accomplish something chemically analogous. If the oxidants produced by radiolysis can be carried downward through the ice, whether by ice convection, through cracks, or by other transport mechanisms, they would deliver a supply of chemical energy into an ocean that otherwise has no access to any external energy source from above. An ocean receiving oxidants from above and mineral-rich chemistry from a heated seafloor below would have a chemical gradient, a difference in energy state between the top and bottom of the water column, and chemical gradients are precisely what living systems exploit. The radiation that makes Europa's surface one of the most hostile environments in the solar system may simultaneously be providing fuel to the ocean below it. The poison and the fuel are the same thing, but for either to reach the ocean, they have to pass through something kilometers thick, something that is not the passive barrier it appears to be. Between the ocean and the space above Europa sits a shell of ice, not a thin crust, not a fragile covering. A shell estimated at between 15 and 25 kilometers thick, made of water ice under enormous pressure, sitting on top of an ocean and below a radiation environment that bombards it continuously from above. Most people, thinking about this shell, imagine it as a wall, a seal, a barrier that keeps the ocean completely separate from the universe outside it. That picture is wrong. The ice shell is not static. It does not sit still. It moves. Think of a pot of water heating slowly on a stove. The water at the bottom, closest to the heat source, warms first. It becomes less dense. It rises. The cooler water at the top, denser, sinks to replace it. A slow circulation establishes itself, driven by the temperature difference between the bottom and the top. Europa's ice shell behaves in a similar way, but on a geological timescale. The base of the ice shell, where it contacts the warm ocean below, is slightly warmer than the top, which faces the cold of space. Warmer ice is slightly softer and slightly less dense than colder ice. Over thousands to millions of years, this warmer, softer ice slowly rises through the shell toward the surface. Colder, denser ice from the top descends to take its place. This slow cycling is called convection. It's not visible on human timescales, but over geological time it moves material. It carries chemistry upward from the base of the shell, where the ice has been in contact with the ocean, and it carries whatever is accumulated at the top of the shell, including the oxidants produced by surface radiolysis, downward toward the ocean. The ice shell is a conveyor belt running between two chemical environments. The most dramatic evidence for this convection is visible on the surface. Chaos terrain like Terra Regio forms when the convection in the ice shell is intense enough, or the shell is thin enough in a specific region, that material from deep in the shell, or potentially from the ocean itself, reaches the surface and disrupts the ice above it. The blocks of ice that have shifted and tilted and refrozen in disorder are the visible aftermath of something pushing upward from below, and that upwelling carries chemistry. This is exactly why JWST found its highest carbon dioxide concentration directly over Terra Regio. The chaos terrain is not just a geological accident. It is a place where the ocean spoke loudly enough to break the ice above it, and when it broke through, it carried carbon with it. The ice shell that sits between the ocean and the radiation above is not a passive barrier. It is an active participant in the chemistry of both environments. What comes down from the radiation environment at the top is transformed and transported into the ocean below. What rises from the ocean is carried upward and eventually reaches the surface. The shell is not protecting the ocean from the universe outside it. It is connecting them. and it has been doing this in both directions for hundreds of millions of years, which means the ocean below has been receiving chemistry from the radiation environment above for all of that time. It has been accumulating, building, reacting, in complete darkness, under enormous pressure, heated from below, fed from above, for longer than anything alive on Earth today has existed. What has it become in all that time? That is the question everything else in tonight's story is building toward. The ocean has been established. The ice shell has been shown as a two-way conveyor. The radiation above has been building chemistry for millions of years. Now the question changes, not whether the ocean exists, not whether it is connected to the surface. Both of those are settled. The question now is what is actually inside it. And the honest answer is that we are still working that out. The ocean of Europa has never been sampled. No instrument has passed through the ice. No probe has drifted in the water. Every statement about what the ocean contains comes either from surface chemistry that we interpret as ocean-derived, or from physical and chemical models built from what we know about the system from the outside. What the surface chemistry suggests is this: studies of Europa's surface conducted by ground-based telescopes and by the Galileo spacecraft have detected spectral signatures consistent with sodium chloride and magnesium sulfate. Sodium chloride is table salt. Magnesium sulfate is a compound similar to Epsom salt. Both are plausible products of ocean water reaching the surface and then having its water slowly removed by the vacuum, leaving dissolved minerals behind as a residue, the way a salt flat forms when a shallow lake evaporates on Earth. If these identifications are correct, and the evidence for sodium chloride in particular has strengthened considerably in recent years through work by Mike Brown and Kevin Hand at Caltech and JPL, then Europa's ocean is a saline solution. It has dissolved salts. How much is unknown? It could be more saline than Earth's ocean or less. The models cannot determine this without a direct sample. The pH of the ocean is a critical unknown. Whether the water is acidic or alkaline shapes everything about what chemistry is possible inside it. Which minerals can remain dissolved, which reactions are energetically favourable, what kind of metabolic processes could operate, all of this depends on pH. Earth's ocean is slightly alkaline, around 8.1 on the pH scale, buffered by dissolved carbonate minerals from the seafloor. Europa's ocean pH depends on what chemical reactions have been occurring at its seafloor over geological time, and those reactions are entirely unobserved. Current modelling produces two broad possibilities. If the dominant seafloor reactions involve iron and magnesium-rich rock interacting with water in a process called serpentinization, the water would be pushed toward alkalinity. If the dominant process is carbon dioxide dissolving into the water and not being efficiently buffered by alkaline minerals, the water would lean acidic. Which of these dominates depends on the rock type, the temperature at the seafloor, and how efficiently the two are balanced, none of which are currently constrained by data. JWST's detection of carbon dioxide now adds one confirmed item to the ocean's chemical inventory. Carbon is present. It has been detected directly, not modelled, not inferred from indirect measurements alone. It is there. And it is reaching the surface in quantities that a telescope can read from 628 million kilometres away. Carbon dioxide dissolving into water produces carbonic acid, which pushes pH in the acidic direction. But alkaline minerals from the seafloor can buffer this effect. The carbon detection does not resolve the pH question. It adds a constraint to the models and confirms that dissolved inorganic carbon is part of what the ocean contains. The inventory, as it currently stands, includes at minimum liquid water, dissolved salts, dissolved carbon, thermal energy from tidal heating, and potentially oxidants arriving from the surface through the ice shell. That is not an empty list. But a list of ingredients is not a guarantee of what those ingredients will produce. Carbon is present in many places in the solar system where life is not. Water covers most of Earth's surface, and life does not exist in every body of water. The ingredients are necessary. They are not sufficient. The question of whether they are sufficient on Europa depends on something we cannot yet measure from here. It depends on what is happening at the floor. At the base of Europa's ocean, there is rock. We have never seen it. We have never photographed it. We have never sampled it. No instrument built by human hands has ever been anywhere near it. Everything we think we know about Europa's seafloor comes from models, from knowledge of how silicate rock behaves under the pressures and temperatures expected at that depth, from analogy with similar processes observed elsewhere in the solar system and on Earth, from the constraints provided by what we know about Europa's interior structure, from the Galileo magnetic data and gravity measurements. What the physics tells us is that the same tidal energy that keeps the ocean liquid above also deforms the rock below. Europa's silicate interior is being squeezed and released on every 3.55-day orbit, the same rhythm that flexes the ice shell above and stirs the ocean in between. In rock, that flexing generates heat. In the right conditions, that heat drives interactions between the water above and the rock below. The relevant process is called serpentinization. When liquid water under pressure comes into contact with iron and magnesium-rich silicate rock, a chemical reaction occurs. The rock absorbs the water into its mineral structure, transforming olivine and pyroxene into a different family of minerals. Heat is released as a byproduct, and hydrogen gas is produced. Hydrogen is a chemical fuel, an organism that can extract energy from the reaction between hydrogen and another chemical compound does not need sunlight. It does not need oxygen in the way surface life on Earth does. It needs hydrogen and something to react with, and a chemical environment that makes the reaction energetically favourable. In 1977, the research submersible Alvin descended to the floor of the Pacific Ocean along a section of the Galapagos Rift where bottom water had been detected at anomalously warm temperatures. What the crew found at 2,500 meters depth, in complete darkness, under pressure that would be fatal to an unprotected person, was something no biologist had predicted: an ecosystem. Warm water was rising from cracks in the seafloor, loaded with minerals and hydrogen sulfide, and surrounding these vents, in conditions that were supposed to be incompatible with anything complex, were tube worms 2 meters long, clams the size of dinner plates, crabs, shrimp, and dense bacterial mats covering every available rock surface. These bacteria were not using sunlight, they were using chemistry. Specifically, they were oxidizing hydrogen sulfide emerging from the vent fluid, using the energy of that reaction to build organic matter. Everything in the ecosystem above them ate those bacteria, or ate things that ate them. An entire food web running entirely on chemical energy in a place where the sun had never shone. That discovery permanently changed the definition of what life requires. Before 1977, the answer was sunlight. After 1977, the answer was energy. Later exploration found another type of vent that is even more directly relevant to Europa. The Lost City hydrothermal field, discovered in the year 2000 by Deborah Kelly at the University of Washington, is not a hot volcanic system. It sits on the mid-Atlantic ridge and is driven not by volcanism, but by serpentinization itself, the same water-rock reaction that physics predicts should be occurring at Europa's seafloor. The Lost City vents produce warm, alkaline, hydrogen-rich fluid. The microbial communities they host are dense and chemically diverse. Michael Russell at JPL has argued for decades that systems like Lost City are not just analogues for where life might exist elsewhere. They may represent the type of environment where life on Earth first arose. The chemical gradient between the alkaline vent fluid and the surrounding ocean water across thin mineral membranes that form naturally inside these vents, mirrors the electrochemical gradient that every living cell on Earth uses to generate energy. Russell proposes that life did not build this gradient mechanism from scratch. It inherited the geometry from the mineral structure of the vent. If Europa has alkaline hydrothermal systems at its seafloor, Europa may have the precise environment that, in at least one well-developed scientific hypothesis, was the origin point for life on Earth. We do not know whether Europa has hydrothermal vents. The seafloor has never been observed. All of the above is inference from physics and analogy, not observation. It is a serious inference made by serious scientists supported by the known tidal energy budget and the known chemistry of similar rock types. But it is not a detection. What makes it particularly significant is this. To find out whether the inference is correct, you need to reach the seafloor of an ocean sitting 100 to 170 kilometers below the base of an ice shell, 15 to 25 kilometers thick, on a moon 628 million kilometers away, inside a radiation environment that would destroy most electronics within days. We cannot do that yet. The floor that may be the most important place in the solar system is completely inaccessible to any instrument currently in existence. What we have is chemistry detected on the surface, pointing downward. If tonight has taken you somewhere you did not expect, we are glad you came along. If this is the kind of exploration that matters to you, subscribe so you never miss where we go next. Let us continue. The seafloor is inaccessible. The ocean chemistry is modelled but not sampled. The ice shell has been read only from the outside. Before we go further into what science is doing to answer these questions, we need to sit inside the ocean itself for a moment, because the conditions there are not what most people imagine when they hear the word ocean. Europa's ocean is not like Earth's. Not in depth, not in pressure, not in darkness, not in temperature profile, and not in its relationship to any source of energy we would recognize as normal. Start with depth. The ocean extends from the base of the ice shell down to the seafloor, a distance estimated at between 100 and 170 kilometers. Earth's ocean has an average depth of about 3.7 kilometers. The Mariana Trench, the single deepest point on Earth, reaches not quite 11 kilometers below sea level. Europa's ocean is more than 10 times deeper than that, everywhere, across the entire moon. Now think about what depth means for pressure. The weight of water above any point in an ocean creates pressure. The deeper you go, the more water is pressing down from above. On Earth, every 10 meters of depth adds roughly 1 atmosphere of pressure. At the Mariana Trench's deepest point, the pressure is about 1,100 times the pressure at Earth's surface. It's enough to compress seawater very slightly, enough to crush an unprotected human body, enough to require specially designed equipment to survive. Europa's ocean is 10 times deeper. The pressure at its floor is estimated in the range of several hundred to more than 1,000 times what we experience on Earth's surface. At those pressures, water itself starts to behave differently. Phase diagrams of water, the maps of what state water is in at different temperatures and pressures, show that above certain pressure thresholds, water can freeze even when the temperature is well above 0 Celsius. Pressure alone can force water molecules into solid arrangements. At the very bottom of Europa's ocean, where the pressure is greatest and the temperature, despite tidal heating, may still be quite cold far from any hypothetical vent, there may be a layer of high-pressure ice. Not the floating ice on top of the ocean, ice at the bottom pressing down on the rock, potentially insulating the liquid water from direct contact with the seafloor. If that ice layer is thick, it limits the serpentinization that would otherwise produce hydrogen. It limits the rock-water chemistry that the hydrothermal hypothesis depends on. Whether it is thick or thin depends on details of Europa's temperature profile that current data cannot determine. Now consider the darkness. No photon from the sun reaches the ocean of Europa. The ice shell above is opaque to all solar radiation. The ocean exists in a darkness that is not merely the absence of a light source nearby. It is the physical impossibility of any solar photon ever arriving. The light that makes almost all of Earth's surface life possible, directly or indirectly, has never touched this ocean. On Earth, even the deepest ocean points are not truly disconnected from sunlight. Marine snow, the continuous slow rain of dead organic material sinking from the productive sunlit surface layers, carries photosynthetically produced energy into the abyss. The creatures of Earth's deep ocean may never see light, but they are fed by it through this chain of sinking carbon. Europa's ocean has no marine snow. There is no sunlit layer above producing organic material that rains down. The energy chain, if any biology is operating one, must begin entirely within the chemical system of the ocean itself, at the sea floor, in the ice space, in whatever gradient exists between the reducing chemistry rising from below and the oxidants delivered from the surface above. If life exists in Europa's ocean, it has never, in any moment of its existence, been connected to sunlight. It evolved, if it evolved at all, in a world where the concept of light has no physical meaning, where there is no day, no night, no bioluminescence meaningful for vision, because there is no visual system that sunlight ever drove the evolution of. Just water, pressure, darkness, chemical gradients, and whatever life has learned to do with them. The conditions are extreme. They are also not by themselves prohibitive. Earth life has demonstrated that pressure does not prevent life. Darkness does not prevent life. Cold does not prevent life. What prevents life, as far as we know, is the absence of a usable energy gradient. Europa's ocean, as we now understand it from the outside, has at least some of the energy gradients that life requires. Whether it has enough, in the right places, at the right concentrations for long enough, is the question that no current instrument can answer. The ingredients that life requires are not complicated to list. Liquid water, carbon chemistry, an energy source. Time, Europa has all four. This has been said many times, and it remains true each time. Those four conditions are, as far as we understand biology, necessary for life, and Europa satisfies all of them. But there is a gap between necessary and sufficient. Having all the ingredients for a reaction does not mean the reaction will occur. Chemistry is full of situations where all the right components are present and nothing happens because the temperature is wrong, or the concentration is off, or the molecules never encounter each other in the right geometry, or some intermediate step requires a catalyst that is not there. Life is not a simple chemical reaction. It is the most complex organized chemistry we've ever found anywhere. And the process by which it arises from non-living chemistry, called a biogenesis, is one of the deepest unsolved problems in all of science. Not unsolved from lack of trying. Unsolved because it is genuinely difficult, and because we have exactly one confirmed example of it happening: Earth. We cannot determine a probability or a mechanism from a sample size of 1. In 1952, Stanley Miller, a graduate student working under Harold Urey at the University of Chicago, filled a glass apparatus with water vapor, methane, ammonia and hydrogen, circulated the gas mixture through a chamber struck with electric sparks to simulate lightning, and let it run for a week. When he analysed the water at the end, he found amino acids, complex organic molecules, the building blocks of proteins, formed spontaneously from entirely inorganic starting materials using only energy. The Miller-Urey experiment was significant. It showed that the chemistry of life is not unique to living systems. Given simple starting materials and energy, organic molecules form on their own. Amino acids are not life. They are molecules that life uses. The gap between a flask of amino acids in water and a living, reproducing, metabolizing cell is vast, and despite decades of work by researchers around the world, that gap has not been fully bridged in any laboratory. Progress has been made. The RNA world hypothesis, supported by experiments from Jack Szostak at Harvard and others, proposes that self-replicating RNA molecules were a key intermediate stage between chemistry and the first cells. Experiments have shown that RNA nucleotides can form under plausible conditions, and that RNA can catalyze its own copying in limited ways. Michael Russell's alkaline hydrothermal vent hypothesis goes further. It proposes not just that life could have arisen in a hydrothermal system, but that the specific chemistry of serpentinization-driven vents like Lost City provides the precise electrochemical architecture that proto-metabolic chemistry first used. In this model, the first metabolism did not construct its energy-extracting machinery from scratch. It borrowed the geometry from the mineral membranes that form naturally inside the vents. If Russell's hypothesis is approximately correct, then a moon with a liquid water ocean, tidal heating, a rocky seafloor experiencing serpentinization, and dissolved carbon chemistry is not just a place where life could survive. It is a place where the conditions for life to first arise may exist. Europa appears to satisfy all of those conditions to the extent we can determine from the outside. But satisfying the conditions of a hypothesis is not the same as confirming the hypothesis. We do not know whether Russell's model is correct. We do not know whether it captures all the necessary conditions or only some of them. We do not know whether abiogenesis is a process that occurs reliably wherever the right conditions are met, or an event of extraordinary improbability that happened once on Earth and may not have happened anywhere else. We have one example of life in the universe, Earth. We cannot calculate a rate or a probability from that. What we can say is this. If you were asked to identify the place in the solar system where the conditions for life to arise are best matched to the conditions we think may have produced life on Earth, Europa would be a very strong answer. That is not a discovery. It is the best evidenced open question in planetary science. On the 14th of October 2024, a spacecraft launched from Cape Canaveral and began moving outward through the inner solar system. Its name is Europa Clipper. It is a large spacecraft by the standards of planetary missions. With its 2 solar panel arrays fully extended, it spans roughly 30 meters from tip to tip, about the width of a standard basketball court. The solar panels have to be that large because Jupiter is far from the Sun, and the spacecraft needs to generate enough power for its instruments in that reduced sunlight. Clipper carries 9 scientific instruments, a magnetometer designed to measure the induced magnetic field at Europa with far greater precision and at far more orbital positions than the Galileo spacecraft managed. This will allow researchers to constrain the ocean's depth, thickness, and conductivity with much greater accuracy than current data allows. An ice-penetrating radar called REASON, built to send radio waves through the ice shell and measure their return, mapping the internal structure of the shell across the full surface of Europa. Where is the shell thinnest? Where do internal water features exist at shallower depths? Where is the ice-ocean boundary? REASON will begin to answer these questions. An infrared spectrograph to map the surface chemistry at a resolution many orders of magnitude higher than JWST, achieved from 628 million kilometers away. The region of Tara Regio, where JWST found the highest carbon dioxide concentration, will be examined from 25 kilometers. The chemical map that Webb produced will become a high-definition image, a mass spectrometer called MassSpex, designed to analyze the composition of any gas or particles that Clipper encounters during its flybys. If plumes are venting from Europa's surface, carrying ocean material into space, MassSpex will analyze what those plumes contain. Clipper is not looking for life. This is worth saying clearly, because it surprises many people. The most promising candidate for life in the solar system is the target of this mission, and the mission is not looking for life. Why? Because looking for life requires a sample, not an image, not a chemical spectrum from orbit, a physical sample of the material where life might exist, analysed by instruments sensitive enough to distinguish biological chemistry from abiotic chemistry with confidence. Clipper is a flyby mission. It will make 49 close passes of Europa over its operational period, spending only brief windows close to the surface before moving away on its Jupiter-centred orbit. Its instruments will characterise the environment with extraordinary detail. But characterising the environment is not the same as detecting life. Think of it as a medical analogy. Before a doctor performs a biopsy to look for disease, they take blood pressure, blood chemistry, temperature, imaging scans. Not because those measurements confirm or deny the diagnosis, but because they tell the doctor whether the invasive procedure is warranted and where to look. Clipper is taking measurements. It is determining whether the invasive procedures, a lander, a drill, a sample return, are warranted and where to direct them. The JWST detection of carbon dioxide over Terra Regio has already done something important for Clipper's planning. It has identified a specific target region on Europa's surface where the ocean surface chemical connection is most directly evidenced. Clipper will examine Terra Regio in detail, characterizing its chemistry, its ice shell thickness, its thermal properties, and its geological activity. The carbon signal that Webb detected as a regional concentration over hundreds of kilometers will become, in Clipper's readings, a detailed chemical map at a scale Webb could not resolve. Clipper arrives at Jupiter in 2030. The flyby campaign runs for several years after arrival. The full data set, analysed and published, will be available through the mid-2030s. What comes next depends on what Clipper finds. If the ice shell is thin enough in specific regions, a lander mission becomes feasible. A lander could sample the surface directly. It could carry instruments sensitive to complex organics, isotopic ratios, and other biosignatures. If plumes are active and chemically rich, a plume sampling mission becomes compelling. But a lander mission to Europa does not currently exist. It is not funded. It is not designed. It awaits the evidence Clipper will provide. The sequence from JWST's carbon detection in 2023 to a lander on Europa to, eventually, something capable of reaching the ocean itself is measured not in years but in decades. Each step requires funding, design, construction, testing, launch, travel, and analysis. Each step enables the next. None can be skipped. Clipper is the next step. Everything before it was preparation. Everything after it will depend on what it returns. The title of this video uses the word terrifying. It deserves an honest examination. Europa is not a threat to Earth. Nothing about what JWST found suggests danger to our planet, our species, or any spacecraft currently in the solar system. The Moon sits 628 million kilometers away and poses no hazard to anything here. The word terrifying in the title is not pointing at danger. It is pointing at something harder to name than danger. Before September 2023, Europa's ocean was the strongest candidate for extraterrestrial liquid water in the solar system. Its existence had been established by the magnetic induction data from the Galileo spacecraft in the 1990s and confirmed by decades of surface geology analysis. Its chemistry was a set of model predictions, not measurements. Scientists could say with confidence that the ocean was probably there. They could not say what it contained, because they had not directly measured what it contained. After September 2023, that changed. The chemistry was no longer only modelled, it was measured. The carbon dioxide over Terra Regio was detected by an instrument with the sensitivity and resolution to locate it spatially, to place it over the youngest, most geologically active region of the surface, to rule out the most natural alternative explanations, and to conclude that the pattern was most consistent with ocean-derived material reaching the surface through the ice. That shift is not trivial. Before the JWST observation, saying that Europa had the conditions for life was a claim based on strong indirect evidence. After the JWST observation, saying that Europa has a confirmed liquid water ocean, with confirmed dissolved carbon chemistry that has been directly detected at the surface, is a statement grounded in measurement. The same ocean was always there. What changed is what we can honestly say about it, without reaching further than the data allows. There is one place in the universe where life is confirmed: Earth. There is one place in the solar system where all of the following are simultaneously true. A liquid water ocean larger than all of Earth's oceans combined exists and is confirmed. The chemistry of that ocean has been directly detected at the surface. A stable tidal heat source has been running for hundreds of millions of years, and the conditions known to be necessary for life are all present. That place is Europa. Both of the possibilities that follow from that sentence remain fully open. If there is no life in Europa's ocean, then the most chemically favourable non-Earth environment we have ever identified is biologically empty. An ocean twice the size of all Earth's seas, sitting in darkness for hundreds of millions of years, with water and carbon and energy and time, and nothing alive in it. That result would force a serious reconsideration of how common life is in the universe. If there is life in Europa's ocean, it has been there longer than complex animals have existed on Earth. It has never been touched by sunlight. It has no connection to the surface above it, no awareness of the ice enclosing it, no knowledge of the planet it orbits or the star that planet circles. It simply exists, in the dark, in the cold, in the pressure, in the only world it has ever known. Both of those outcomes are, in their own precise way, disorienting to hold in mind at the same time. That is what the title is pointing at. Not danger, vertigo. The specific kind of vertigo that comes from standing at the edge of the largest open scientific question in human history, and knowing that the question is now more specifically evidenced than it has ever been, and that the answer is still decades away. The sequence of events that led to where we are now moves slowly, but it moves. In 1610, Galileo Galilei noticed 4 points of light near Jupiter that moved from night to night in a line. He understood that they were orbiting Jupiter. He did not know what they were made of, how large they were, or what was happening inside them. He simply noticed that they moved. One of those points was Europa. For the next 3.5 centuries, Europa remained a number in an orbital table. In the 1990s, the Galileo spacecraft read the Moon's electromagnetic signature and inferred a global ocean of salt water beneath the ice. Europa became a world with an interior. In 2013, the Hubble Space Telescope detected what appeared to be plumes of water vapour rising from Europa's south polar region, roughly 200 kilometers above the surface. The detections were intermittent, faint, and difficult to characterize, but they repeated. In 2016 and again in 2019, similar features appeared in Hubble's ultraviolet data over the same region. If those plumes are real, they are significant beyond their own observation. Enceladus, a small moon of Saturn, has active plumes confirmed beyond any doubt by the Cassini spacecraft. Cassini flew through those plumes multiple times and analysed them directly with its mass spectrometer. The results found water ice, salt, silica, hydrogen gas, carbon dioxide, methane, and complex organic molecules. Organics and hydrogen together pointed at hydrothermal chemistry occurring at Enceladus's seafloor, producing compounds that were then carried through the plumes into space, where Cassini collected them on the fly. No drilling required, no lander needed. The Moon was sending its ocean chemistry directly into space, and a spacecraft read it. If Europa's plumes are real and are carrying ocean material into space, Europa Clipper, making 49 close flybys starting after its arrival at Jupiter in 2030, may be able to do the same thing. Flying through a Europa plume at 25 kilometers altitude with a mass spectrometer running would deliver direct ocean chemistry to an instrument without touching the ice. What Clipper would find in a plume would not confirm life, but it would characterize the ocean's chemistry at a level no orbital observation from any distance has achieved. Salts, organic compounds, hydrogen, carbon species, all of it readable from the outside if the ocean is actively sending it out. The question of whether Europa's plumes are real is one of the most important things Clipper's instruments are positioned to answer. In September 2023, James Webb Space Telescope contributed to this sequence. It did not detect plumes. It detected what the plumes, if they exist, would also be expected to reveal: the chemical fingerprint of an ocean interior leaving its mark on the surface. Carbon dioxide concentrated over the youngest, most geologically active region on the Moon. A reading of the ocean's chemistry from the outside through the ice. The sequence continues. Each observation adds a layer. Each instrument reads something the previous one could not. And each reading narrows the question without yet answering it. We are still in the middle of the sequence. The question of life on Europa is not yet an answered question. It is not even close to an answered question. What it is, as of September 2023, is the most specifically evidenced open question in planetary science. A question with more confirmed relevant data behind it than it has ever had. A question with a spacecraft on the way to gather more. But the answer itself is not at the end of Clipper's mission. It is at the end of a sequence of which Clipper is the next step. To understand how far the answer still is, it helps to trace the chain of access that leads from where we are to where the answer lives. The answer lives in the ocean. Specifically, it lives in whether the ocean's chemistry includes anything that can only be explained by biology. Biological chemistry leaves distinctive marks, certain isotopic ratios, certain molecular complexity patterns, certain organizational structures. The specific combination of compounds that life produces as it metabolizes and reproduces is not easily mimicked by abiotic chemistry. To detect those marks, you need a sample, not a spectrum from orbit, not an image, not magnetic field reading, a physical sample of material from the environment where life might exist, delivered to instruments sensitive enough to distinguish biological chemistry from geological chemistry. Getting that sample from Europa's ocean requires passing through the ice shell. The ice shell is between 15 and 25 kilometers thick. Drilling through 15 kilometers of ice is an engineering challenge without precedent. The deepest borehole ever drilled on Earth, the Kola Super Deep Borehole in Russia, reached approximately 12 kilometers into the crust over a project that ran for more than 2 decades. Drilling through Europa's ice would face not just the depth challenge, but also the radiation environment, the power requirements, the communication delay, the sterility requirements to prevent contaminating the ocean with Earth organisms, and the complete remoteness from any human repair team. No such drill exists. No mission carrying such a drill has been funded or designed. What does exist is a sequence of steps, each one enabling the next. Clipper characterizes the ice shell, maps its thickness, identifies the most promising entry points, and determines whether plumes offer a shortcut by sampling ocean chemistry from above the ice. Clipper's findings determine whether a lander mission is warranted and where it should land. A lander, if built and sent, samples the surface directly. If the surface samples are compelling enough, a mission with drilling capability is proposed and eventually built. Each of those steps adds a decade or more to the timeline. Clipper arrives in 2030. full data analysed by the mid-2030s. A lander mission, if approved based on Clipper results, might launch in the late 2030s at the earliest and arrive in the mid-2040s. A drill through the ice, if a lander mission produces results compelling enough to justify it, is a project for the latter half of this century at the earliest. The answer, if it comes in our lifetimes, will arrive very late in our lifetimes. But here is what that timeline means for right now. We are the generation that first read the chemical fingerprint of Europa's ocean from the outside. Geronimo Villanueva and his colleagues at Goddard published that reading in September 2023, and it placed a direct measurement of ocean-derived chemistry in the scientific record for the first time. Before that, the ocean was inferred. After that, its chemistry was directly detected. That is not nothing. That is the first word of a long conversation. A conversation that will run for decades, conducted by instruments that do not yet exist, asking a question that may take a century to answer. We began it. We sent the first instrument that was capable of reading Europa's chemistry from the outside. We found carbon. We placed that finding in the scientific record, and we launched a spacecraft to follow up. Whatever the answer turns out to be, it will be found at the end of a chain of inquiry that started here, with a gold mirror telescope in the dark between Earth and deep space, pointed at a small frozen moon for 53 minutes in September 2022. If this kind of deep, patient exploration of the universe is what you come here for, subscribe. We will keep going as far as the questions reach. Now let us finish this together. There is a question that science has not yet been able to ask cleanly, because the tools to ask it do not yet exist. Not whether life is on Europa. That question requires a sample. We have established that. The question before that one. What would we even be looking for? It sounds simple. Detect life. But detecting life requires knowing what life looks like when you cannot observe it directly, when you can only read chemistry, when you cannot see cells or organisms or behaviour, when the only thing you have is a sample of fluid or surface material and a set of instruments. On Earth, detecting life in a sample is not always straightforward, even when the sample is from Earth. Certain metabolic byproducts accumulate in environments where life is active. Specific isotopic ratios of carbon and sulfur and nitrogen shift when biology is processing those elements. Certain molecular complexity patterns, chains of organic molecules with specific chirality, meaning a specific handedness in their three-dimensional structure, are produced by biology and not efficiently produced by abiotic chemistry. Amino acids, for example, exist in two mirror image forms called left-handed and right-handed. Abiotic chemistry produces both forms in roughly equal quantities. Biology on Earth exclusively uses left-handed amino acids. If you found a sample in which nearly all the amino acids were left-handed, that would be a strong biosignature, a chemical pattern that strongly suggests biological origin. But biosignatures are not confirmations. They're probabilities. They shift the probability that biology is present. In some cases, they shift it very significantly. But unusual chemistry can sometimes arise from unusual geology, and a claimed biosignature on another world would face an enormous burden of proof before the scientific community would accept it. The instruments aboard a Europa lander, if one is designed, would need to search for multiple independent lines of biosignature evidence simultaneously. Not just one unusual compound, not just one shifted isotopic ratio. A pattern of chemistry that, taken together, is most plausibly explained by biology, and least plausibly explained by the known range of abiotic processes. This is not a solved problem even for Earth samples. For samples from a moon whose geological chemistry we do not fully understand, it would be significantly harder. Kevin Hand at JPL, one of the leading researchers in astrobiology and Europa science, has spent years thinking about exactly this problem. What would a lander need to carry? What measurements would be most diagnostic? What combination of results would be convincing? His work, and that of his colleagues at JPL and elsewhere, is shaping the instrument concepts for a potential future Europa lander. The answer that Hand and others have converged on is not simple. Detecting life on Europa would require a campaign of measurements, not a single instrument reading. It would require ruling out geological explanations for every unusual chemical signal found. It would require multiple independent biosignatures pointing in the same direction. And even then, the scientific community would debate it, as they should. The detection of life beyond Earth would be the most consequential scientific claim in human history. It would require the most rigorous evidence in human history. One unusual chemical in one sample would not be enough. 10 unusual chemicals in 10 samples, all pointing the same way, analysed by multiple independent research groups, replicated and verified over years, would begin to build a case. That is the standard of evidence the question deserves. We are not there yet. We do not have a sample. We do not have a lander. We barely have a characterization mission on its way. But knowing what we are looking for, and how hard it will be to confirm when we find it, is part of the story. Step outside on a clear night and look for Jupiter. Depending on the season and your latitude, it may be one of the brightest points in the sky. A steady, constant light, not twinkling the way stars do, bright and calm. Near Jupiter, visible in binoculars if the sky is clear, there are 4 small points arranged in a rough line through Jupiter's equatorial plane. They shift from night to night. Galileo watched those same points 4 centuries ago and understood that they orbited Jupiter. It was one of the observations that began unravelling the model of the universe that had placed Earth at the centre of all motion. One of those 4 points is Europa. From where you are standing, you cannot see anything of what we have been talking about tonight. You cannot see the fractured ice, the long dark lineae stretching for thousands of kilometres, the reddish chaos terrain of Terra Regio, where an ocean's chemistry has been pushing upward through the ice for millions of years. The distance collapses everything into a single point of reflected light, smaller than the period at the end of this sentence. Inside that point is an ocean, not a lake, not a pocket of water, an ocean. One that contains more liquid water than every ocean on Earth's surface combined, sitting in total darkness beneath 20 kilometres of moving ice, kept liquid not by sunlight, but by the gravitational engine of the largest planet in the solar system. An ocean whose chemistry was directly read for the first time in September 2022. A telescope parked 1.5 million kilometres from Earth spent 53 minutes collecting infrared light reflected from the surface of that moon. In the data that came back, there was carbon, not scattered, not random, concentrated over the youngest, most geologically active region on the surface, pointing downward toward an ocean we've never touched. The signal does not say life is there, it says the ocean is active, the interior is communicating with the surface, the chemistry is real, the system is not sealed and static. It is alive in the purely geological sense, participating in the chemistry of the moon above it, sending material upward, receiving material downward in a slow and cold and dark exchange that has been running for longer than complex animals have existed on our own planet. Whether something else is alive in it, in the biological sense, is the question. It is a question with more direct evidence behind it now than it had before September 2023. It is a question that a spacecraft launched in October 2024 is currently travelling toward, making its slow way through the inner solar system, carrying 9 instruments, scheduled to reach Jupiter in 2030. It is a question that will not be answered by that spacecraft. It will be answered, if it is answered in our lifetimes at all, by something that follows Clipper, something that lands, something that drills, something that touches the ice or passes through a plume and carries the ocean's chemistry back to an instrument that can read what it contains. That instrument does not exist yet. The mission that will carry it does not exist yet. The answer waits in an ocean under kilometers of ice on a moon orbiting a gas giant more than 600 million kilometers from Earth, in a darkness so complete that no photon from the sun has ever reached it. We know it is there. We have read its chemistry from the outside for the first time, and the next time you see Jupiter in the night sky, holding steady above the horizon while everything around it twinkles and shifts, find the small points near it. One of them is Europa. That point is not just a moon. It is the place in the solar system where the oldest question we have ever asked is most specifically evidenced. Are we alone? We do not know yet. But we are for the first time asking it with data in hand, and we will keep asking until we have an answer. Take care of yourselves tonight. Look up when you can. The universe is quieter and stranger and more full of possibility than it appears from here. Good night.